All right, we're going to start Unit 6, Integration, using the integral. The integral will calculate area, volume, and distance traveled. In this unit, we're going to approximate area under a curve using Riemann sums. We're going to apply the fundamental theorem of calculus, use integral properties to solve integration problems, and use substitution, completing the square, and long division to solve integration problems. So Riemann sums, we're approximating area using geometry. The area of the region between the graph and the rate of change function. So the rate of change function is the derivative, f prime of x. And the x-axis gives the accumulation of change. So it's the graph of the derivative between the graph and the x-axis. We get the total accumulation of whatever the unit is. If the rate of change is positive over the interval, then the accumulation change will be positive. If the rate of change, so the derivative, is negative over the interval, then the accumulated change will be negative. So the definition of a definite integral. If f is a continuous function between a and b, then the definite integral for f from a to b is, so this is the notation we use and we're comfortable with. The limit notation you need to know if you're taking the AP exam. So this is called a summation. There's probably two M's in that, where we're adding all the terms together. But if we take the limit as n approaches infinity, well, then we're adding infinite terms together, and that's what the integral does for us. So if y equals f of x is continuous and non-negative over a closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by, so area is calculated with a definite integral. Area between a and b can be calculated using a definite integral. If f of x takes on both positive and negative values over a closed interval, then the area of the region bounded by the graph and the x-axis is attained by adding the absolute value of the definite integral over the sub-interval where f of x does not change sign. So area is never negative. Area is always positive. So if I wanted to know this total area, I would take A1 plus the absolute value of A2 plus A3 would be the total area between A and B. The figure above shows how both the total area and the value of the definite integral can be interpreted in terms of the area between the graph of f of x and the x-axis. The definite integral between a and b would be a sub 1 minus a sub 2 plus a sub 3. The total area between the curve and the x-axis is the absolute value. So then we're going to add all three together. We add the areas together. Even if they're negative. So applications of definite integrals. If the population density of a region at a distance x from the straight road is d of x, so we have distance, then the total population of the region between x equals a and x equals b is given by that definite integral. So we'll go over these when we do applications of integration. So in some cases, accumulation of change can be evaluated using geometry. Definite integrals can be approximated using left Riemann sums, right Riemann sums, midpoint Riemann sums, and trapezoidal Riemann sums. Left, right, and midpoint all use rectangles to approximate area, and trapezoidal sum uses trapezoids to approximate area. Depending on the behavior of the function, it may be possible to determine whether approximation is an over or underestimate. So we can always determine over or underestimates for left, right, and trapezoidal, but we don't determine over or underestimates for midpoint, because a midpoint Riemann sum, well, here's a graph of one here. Yeah, so the area is being calculated at the midpoint of each, the height's being calculated at the midpoint of each of these intervals, at least up till there. Yeah, where we have some area over and some under, so it's not easy to determine whether it's an over or under approximation. A midpoint approximation is usually pretty close to the actual area. So, to find delta x is the change in x. So often the width of the rectangle or the height of the right trapezoid. Delta x is equal to b minus a over n. So the change in x is equal to b minus a over n, where n is the number of subintervals. So the number of rectangles or the number of trapezoids. So we know what a rectangle looks like. So the width, again, is b minus a over n. The height is equal to f of x. So if I'm finding a left hand, let's label these both a and b, starting at a, ending at b, we'll just leave it as one rectangle. If I'm going to find a left-hand approximation, then I'm going to use the height from the left side of the triangle, which would be f of a. I would use f of a for the height if I was using a left-hand approximation. If I was trying to find a right-hand Riemann sum, I would use f of b, the height at b, the left side of the rectangle. And a midpoint, I would use the average, b minus a divided by 2, and I would find the height at the midpoint. A trapezoid, so when you think of a trapezoid, you're probably thinking of this shape. Definition of a trapezoid is two parallel lines, one set of parallel lines, I should say. One set of parallel lines. It's quadrilateral with one set of parallel lines. So our bases are the parallel lines, right? So here we have a vertical trapezoid. And here we would find the height from this right angle. Well, our height, our right angle, is along the x-axis. So the height is equal to the width, again, b minus a over n. The area of a trapezoid is 1/2 times the base plus the base times the height. So in function notation, right, if this is x sub 1 and this is x sub 2, the two x values, then the bases would come from f of x sub 1 plus f of x sub 2 times the width. I put w in here because that's the same width as in the rectangle. Right, the width is along the x-axis. The whole thing divided by 2. If you're taking the AP exam, we'll go over this notation more. Again, it's just the definitions with the summation notation, but they're just not very fun to look at. So this is an example of a left hand using left hand endpoints. So here we have 4 subintervals, right? We have 4 rectangles. A is equal to 1, B is equal to 5. So the width is equal to 5 minus 1 divided by 4, which is 1. So the width of each rectangle is 1, and the height is different. So the height is f of 1 for the first rectangle, right? Going up at 1, and that's the height of that rectangle. The height of the second rectangle is at 2. So f of 2 is the height of our second rectangle. F of 3 is the height of our third rectangle. And f of 4 is the height of our fourth rectangle. Notice how the 5 gets left off. I have 5 values, but I only need 4 rectangles, so I only need 4 heights. So the rightmost value will be left off. We find the heights at 1, 2, 3, and 4. Multiply each by the width, which in this case is 1. And there's it worked out for you. The right-hand endpoints work very similar. So again, we have 4 subintervals between 1 and 5, so our width is equal to 1. This time we're going to find the height at the right side of each rectangle. So f of 2 will be the height of our first rectangle, f of 3 the height of our second, f of 4 the height of our third, and f of 5 the height of our fourth. And then it's all worked out here for you to look through. So the true area, we can see that this left-hand approximation is an over approximation. Right, the actual area is the area between the curve and the x-axis. So what I'm highlighting here in orange, exactly between the curve and the x-axis, that would be the exact area. Well, these rectangles go over that area, so we have an over approximation. Here we have an under approximation. And we know that the actual area, the true area, is between these two. So we could take their average and get closer to it, but we know it's between these two values, the left and the right hand. So let's do an example. So we have selected values for f of x shown in the table. What is the left Riemann sum approximation between 3 and 6 using 3 subintervals as indicated by the table? So 3 equals n. And it says as indicated by the table. If I wanted widths of equal length, then I would do 6 minus 3 divided by 3, which equals 1. Now it says as indicated by the table. So therefore, I have to use the widths they give me, which in this case is 1. It's increasing by 1, but that's not always the case when given a table. So the area of our first rectangle, the width is always 1. But my height I'm going to take from the left hand endpoint, and my height is 6. So the area of this first rectangle, there's no reason to draw the rectangle, I'm just going to write it out. Area of the first rectangle is 6 times 1, which equals 6. Area of my second rectangle is 9 times 1, which is 9. And area of my third rectangle is 12 times 1, which is 12. So my approximated area, I'm approximating the area between 3 and 6 of f of x dx. My approximate area is 6 plus 9 plus 12. So approximately 27 units is that area. Let's try another one. Okay, well, f be the function defined by f of x equals 3 root x. If 6 subintervals of equal length, so n equals 6, what is the value of the right Riemann sum approximation between 1 and 7 of this function? So let's find the width. b minus a over n. So we're going to get 6 over 6, which is 1. That's nice. So now, If the width is 1, and I'm finding right-hand approximations, then I'm going to have to find the heights at 2, 3, 4, 5, 6, and 7. So this will be approximate. If my width is 1 and I have to multiply by 1, nothing's going to change. So I'm just going to be writing my heights out. So I need to find f of 2 plus f of 3 plus f of 4. Notice we have 1, 2, 3, 4, 5, 6 heights that we're adding together, and I needed 6 subintervals. So 6 rectangles. The 1 is left off because it is the leftmost endpoint, and we needed to use the right in this case. So use your calculator to find this value. I got 37.433 units approximating that area. We're going to find the midpoint Riemann sum approximation between 3 and 6 using 3 subintervals. So only 3 rectangles as indicated by the table. So between 3 and 4, my midpoint is 3.5. So we're going to use that height. Between 4 and 5, my midpoint is 17. I'll use that height. And between 5 and 6, my midpoint is 5.5. And the height is 13. So again, my width is 1. Between 3 and 4, between 4 and 5, and between 5 and 6, my width is 1. So I just need to add these heights together to approximate this area. And that looks like 49, I believe. Yep. All right, and you can do this one on your own. Oh, this is trapezoid, never mind. Okay, we'll work this one out.